for indication to the problem. And since this is the workshop for Coulomb branch and DAHA, so I try to, I will explain the something which is intersection. So this is all, and of course, all the result, even Baranina and Basel realize DAHA as a kind of by study by Steinberg variety for the R5 flag variety. That is before the Coulomb was introduced. But I at least so the first part of my talk is the review of this old result. But at the end, I'd like to add something new, which is a realization of C-check C-DAHA, which we just had in the previous. Okay, so I first recall the definition of Coulomb branches, which we already had in the morning. So you start with G and M. So G is complex reactive group, and M is symplectic representation. And I assume M is of potassium time. So N is a complex usual representation. Then you assign two symplectic varieties to this. So one is the Higgs branch, which is easier to understand. So this is a symplectic reduction of M by G, which I denote by M triple slash G. So you have moment map and take the zero inverse image and take categorical quotient by G. So this is Higgs branch. I might denote by M of H. If I want to emphasize G and M, then I denote. Then we can also go to the Coulomb branch. So this is I denote by MC. Or I may like G of M or G of N. So this is spectrum of the convolution algebra of invariant cohomology. So O is a formal power series, and K is formal Roland power series. And we consider G of O and G of K. And also N is a representation, we also consider N of O and N of K. Then we consider two spaces T and R, as Eugene explained. So this is a vector bundle over Grassmannian, whose fiber is N of O. Grassmannian. This is the vector bundle. Fiber is equal to N. And here you have projection to N of K. So which is just given by if you have G of Z and S of Z, then you just multiply. Then R is the inverse image of N of O. So you know this map by P. Then this we consider this as an analog of the spin resolution, and I take a fiber product of T of N K, and this is the analog of Steinberg variety. And if I consider G of K, so this should have convolution product as usual. But the technical reason we cannot make rigorous this definition. So we replace this one. By formally applying the induction theorem, the equivalent homology, we get double this one. So basically we have the point is, yeah, I think this is just basically by for this reason is that T divided by GK is equals C. So this is basically same as O divided by 0. So from this you can. So anyway, fortunately, we can define the convolution product simply only in terms of R. So this is also cool. And we show that this is a commutative algebra, and we take it. Commutativity is not trivial, but it's an avatar of the geometric Satake correspondence. So this construction is very similar to geometric Satake correspondence, and in that case, the tensor category is commutative because this is isomorphic to the category representation of the Lagrange algorithm. And we also consider quantization. Quantization here means the deformation quantization. So this commutative algebra has a non-commutative deformation. So you consider C-star loop rotation. You just multiply D by 1. So it acts on the on C of also on K and also of G of O and G of K, everything. It acts on everything. So you can consider instead of this equivalent homology, you can consider H star of G of O is the root of R. So this is a non-commutative deformation. So we call this as a quantized Coulomb branch. In my talk, it is also important to consider deformation in both commutative and quantum case. This is given by Flavors. Sorry. This is also explained by Legion, but I would like to recall it. Flavors. So suppose larger group G tilde containing G and a normal subgroup. We have representation and suppose this symplectic representation extends to representation G tilde. And also if M is equal to N plus N star, then G tilde acts on N. Then on the Coulomb branch, Higgs branch side, so G of F, this is G tilde divided by G. So this acts on H. because M of H is defined as a quotient space by G. So if you have a larger group action, then the quotient will act on the quotients. So this is clear. And for the Coulomb branch side, so we consider equivalent homology of larger group, G tilde of O. So G tilde of O acts on this space R. So you can consider equivalent homology for larger group. So then you have more the spectrum of H star of G of F point by structure homomorphism equivalent homology. So this is something E algebra of the maximal torus of G of F divided by Y group. Basically, I only consider the case when this quotient is torus. So this case Y group. And if you take the inverse image of 0, so it means that we just ignore this additional group action. So you get of H star of 0. So this is by definition is Coulomb branch. So in this sense, the Coulomb branch Coulomb branch has a deformation parameterized by equivalent homology of the Fleck symmetry. And in some cases, I mean, of course, it could be trivial deformation, but in many cases, this is actually universal Poisson deformation. And the quantum case, it's same, basically same. We just consider each. So this is analogy over H star point. So in the case of DAHA, so this is one of the parameters. GF is C star in this case. In that case, two parameter arising in this. This is parameter deformation parameter. And what else? So that this construction works also for equivalent decay theory.
Say just one more word about you replaced the Steinberg by R. It's something standard, but what's this statement that there's a map in one direction and
I'm not sure, so I cannot make sense of this. I just use this as a how to say some intuition for this conversion.
okay, and I should
I really don't. Yeah.
Defined, then it should be the same as
If this is appropriately defined, and if you apply the formally the equivalent, how to say, the induction theorem in the equivalent homology, then you arrive at this definition. And then I start with this definition because I don't know how to justify this definition.
R is like the union of the conaural bundles to the G orbits in the flag bracket. Under the
Yeah.
like a skeleton. Okay, thank you.
Okay, this is the general case. And then for DAHA, this is section 1, maybe. So this is very simple. So you just take N to be adjoint representation. And G tilde is just equals C star. So this C star acts on N by scaling. So we take these examples. Then the point is this T. In this case, T is basically cotangent bounded to a fungus one. So it becomes more closer to the usual finite dimensional finger theory. And in this case, or more precisely, very similar situation. Barcelona studied the equivalent case theory of this kind of setting. Other than the definition Coulomb in general was given. The H means A star A of G of. Maybe in that case, your horizon. One more parameter. R or affine plug bar. Instead of affine plus manion. So then, in this case, even if you kill this loop rotation, this is still non-commutative. And in fact, they prove that this is DAHA. DAHA or of type. The affine. Maybe I still don't understand the notation for the type of DAHA. So I hope this is clear. So you consider the real algebra and you consider untwisted affine real algebra. So I probably this. So this has two parameters, Q and T. So this is quantum parameter fit. So this is coming from the root rotation. This. Okay. So this is the result. So our result is the definition is variant of this. So we have
What's the type? G.
yeah, fine.
Yeah.
Untested offer. I still don't understand that. I still have trouble to read
But if you-
McDonald's book.
Say double affine. Then you don't-
Double affine. I think, but I think that as far as you read McDonald's book, I think that if maybe type G1 and something, I still don't understand. there is a affine root system, but maybe somebody could tell me this.
Clarity, this is a thing that has a finite Heck algebra and two lattices.
Yeah, that I think I understand, but
I know you know. Just confirming that we mean the same thing.
yes, but I don't understand completely. So. I'm not sure where this determinant is proved, but I think this is true. With the Coulomb branch. Because of the difference between the log and Grassmann, to see that the slightly different. This is we just get spherical part. And is quantized. And if you just replace homological one, then this is some of it spherical part of trigonometric graph. So what the difference between the DAHA and the trigonometric DAHA is illustrated by considering the designation when both once you Q the both parameter Q and T. So if you go Q both Q1, then you get functions on E plus T check. T is much more torus divided by Y group. And the trigonometric one is you just replace I think this is right. T plus T check. Now we consider the case G is equal to GLN.
What are the Q and T parameters here? Where do they come from?
This is the loop rotation and the scaling. T is the flavor symmetry. Is it clear?
Usually you consider like this combination of loop rotation and scaling.
If you so this is for this case is a quiver case and you have a loop, and then you cannot kill the scaling. But if you consider the
sorry, it's in the non-simply laced case. You still only have one T.
yes, still I still don't understand. Yeah. Question is a quick answer is I don't understand, but C check somehow C check C which I will describe is more universal, more parameters, and maybe may have some chance to do the specialization from C check C. But still I don't understand. Yes.
The theory is K cohomology, right? Sorry, I'm trying.
K homology. K homology. So this is the homology.
With the K.
K homology. So this is an example. This is an example of what we call divergence. So if you are given quiver, so in this particular case, this is a so-called Jordan quiver. So you put a vector space on this vertex, and group is, in this case, you only have a single vertex, but if you have several vertex, the group is a product of general linear groups, and n is a homomorphism assigned for each arrows. And in this case, yeah, if you are familiar with the theory of equivalency, so this quiver is not behaving well, and it is better to have the so-called framing. So maybe here people usually denote the dimension of vector space by n circle. So I take two integer n and r, and I consider this quiver. And there are two types of vertices. One is a circle and one is sphere. And for square one, you don't include it in the group G, but you include it in the Flavor symmetry. So in this case, what is G? So first of all, n is GLN plus Cn, and then some R copies. And the G is the same GLN, but G tilde is G cross. Maybe I take just to take the maximum. R, but in fact, the overall scaling is absorbed in GLN, so you should divide by the diagonal one. And times this. So this is this is an example. Again, this is an example of group and its representation.
Why do you have to divide by sister?
Because I mean, overall, if you just diagonal scaling, then it could be absorbed. It could be just regarded as a scaling matrix, scalar matrix in here.
Right, does this theorem give you nice bases of the spherical DAHA? Or bases with nice property?
I think this is it's interesting question, but maybe this particular case, this has a cluster structure. Not in this particular case. This is a case of this the group. The representation is when the representation is there. Yeah, that I'm not sure. Yeah, I don't know. So you consider the categorification of this by saying the Papa's coherent sheaves on this variety and okay, then Higgs branch. This is all the results. AHM at the hitching during the money and those to person. It is maybe 70s to 80s. So you consider the Higgs branch, which is n plus n star and G. So this is the so-called Uhlenbeck partial compactification. Of claimed instant modular space. Or OS4, which is 1-point compactification R4. So instant is a certain nonlinear partial differential equation which has been studied by many people. And so I don't want to go into detail with this, but it also has algebra definition, so compactification of framed rank R holomorphic vector bundle over these. Which is a compactification of C2 in line at the end. The framing means that here framing means the trivialization of the boundary. So this translates is trivialization of the this is some nice space which people have studied. And the Coulomb branch in this case this is serum. Again, I'm not sure who proved this. Okay, anyway, so this is the symmetric powers of the so-called AR minus one surface. Sorry, AR minus one surface. N times, and then divide by C. So R is this R for dimension of the framing and every dimension for the dimensional. And the R minus surface is defined by X, Y, e to the R. So I think A minus one is not really considered, but this in this equation, C plus C star, and A of 0 surface is C2, and AR starting from R is usual.
It'd be A0 and 1.
A0 is oh, maybe let me see what is wrong. C star equal minus one. This should be
Minus
correct.
one is-
Maybe
That's right. Minus one is just C star cross C star.
R equal R minus one. No, something is wrong.
No, I think you're right. If R is
right.
2, then you get it as one singularity, right?
Because this R and this R, this is R minus and this is R. And also in this case, the deformation of this is well known. Poisson deformation. Is R minus one for n equal one, and then equals greater than one, you have one more dimension of the function. So this, and this, as I said before, realized by diversity. Very nice case, and we studied its consideration.
Really holomorphic vector bundles there for torsion free.
Then you get different. So you put the stability condition in here. Then you get the modular space of torsion-free shapes. But I defined Higgs branch as the categorical quotient. I'm sure I proved this. So in this case, counter is Coulomb branch. Speaker. Cyclotomic DAHA. Or rational algebraic algebra. Associated to this product. So rational algebraic algebra was cyclotomic DAHA was introduced by Ginsburg as a quantization of the the spherical. I mean, first take smash product of the Rn by Sn, and its quantization was defined by Ginsburg as rational algebraic algebra. And since we are considering spherical, the corresponding ring is this the coordinate ring of exposure.
I'm kind of surprised it's rational, but before you had non-degenerate and trigonometric, why would rational appear?
Yeah. So it's a little bit complicated. So R equal 1, R equal 0 case. So this is the previous case. We get the trigonometric one. That's great. And for R equal 1, then this part is then you get the rational DAHA.
But you still take a theory, right?
Huh?
You still work with a theory rather than.
No, this is the homological one.
But I thought, so the quantization is not from the Q and the K theory, but
So this is a stop. C stop. Point. So this is. Well, I usually do it.
I see. Oh, I see.
Q is the exponential of it. So in this case, the T cross. T check T divided by W, and in this case, further replace T. And R greater than 2, so you get. And you can consider also the theoretic version. So this was studied by Graham and let's think about. So for R equal 0, you get the usual DAHA. And for R equal 1, this is trigonometric one. But from R greater than 2, it seems they say that this is a new algebra. Maybe I just want to comment on their proof for this. So the proof for this commutative statement is where it is. This is something I don't want to explain. So we just know that this should be the Coulomb branch, and there are some criterion which Coulomb branch should satisfy, and I just to check this basic status. It's not really mean. But at least for this continuation, once you know that this then somehow in fact, this key ingredient is already appeared in the appendix of one of the PFM paper. It is a minuscule monopole operators. Which I think originally appeared in physics literature. I'm not sure who was injecting this. But anyway, the point is, suppose lambda is minuscule coed. I don't remember the definition of minuscule coed. Anyway, so this is, there are not so many, but for general linear graph, we have also. Then the conclusion is, so you have the Affine-Grassmannian, you recall that Affine-Grassmannian has the Schubert cell decomposition, where lambda is dominant coed. And for minuscule, right? So this is close. This georbit is close.
That's a definition. That's one definition.
That's one definition. Yes, that I remember. So good lambda, good G has many components, and you consider for each connected component you choose the smallest one. That is correspond to it. Then so you just take the inverse image. We have this homomorphism from the space R to the Affine-Grassmannian. So then you consider the P inverse of G of lambda. So in general, this is difficult to understand, but if this is closed orbit, then this is can be computed. By the localization or for equivalent case area equivalent modes. So then, so you replace the space R by the fixed point sets by the localization. So you replace the space by its fixed point set, and you just study what this is basically essentially the Affine-Grassmannian T. And the equivalent quantized Coulomb branch for this is just ring of difference operators. On T. So this is a quantization of T cross T check. T cross T check. T check cross T. So this is the cotangent bundle to tangent to T check. So natural quantization is a differential operator on T check, but by you considering the Fourier transform, you consider it a differential operator. And since T appears in the equivalent homological space, so it's natural to consider it's complex to T. So you just compute this operator by localization, then you get McDonald operator. And this argument can be slightly generalized. So if lambda is minuscule, this is smooth. And there's a notion of small covariance, which I completely forget the definition. So in that case, the closure has not canonical resolution. And using that, you can compute similar thing. And the McDonald operators for small covariance is known, and we just identified it. That is possible. Okay. Then
Small is quasi-minuscule, no?
I think small is slightly more general, but it's still small, so not arbitrary. Okay. The remaining 13 minutes, I will talk about the new examples.
Everything by convolution. You get all of the non-minuscule orbits.
Yeah, by just the designation argument. So we have the correct size at Q equal 1. But still, we cannot avoid this annoying result for commutative. So we consider the more general case, and natural candidate is consider ABHM description or ABHM quiver. Description is better. For classical groups. And this generalization of the ADHM description for classical groups is known. I mean, it's already obtained by Hitchman. So in the previous case, we to this quiver, so we take the double, so maybe better to both arrows. So we have B1 and B2 and these. So we put CR symplectic group, symplectic structure, or orthogonal instanton. And CN, we put different opposite one. So if you choose symplectic structure, then Cn is orthogonal vector space. So we put this. And then impose the following condition. B1 star is equal to B1, and B2 star is equal to B2. And B is A star. So we impose these conditions, then it describes the modular space instance for classical groups. Then so we assume So from now, we assume n is even and r is even, and we replace n by 2n and r by 2r. So we consider this situation. And we consider the symplectic case. So G is SP of 2n and C2R. So this is a orthogonal space, but I want to consider this as a cotangent type. So I decompose it into CR and CR star. So this is isotropic subspace. Then this M is of this form, n plus n star. So n is just B1 and A. So B1 satisfies B1 star equal B1. And maybe the bar is CR here, instead of C to R. We take a half. Okay. And G is this. So, and the flavor symmetry. So this is the maximal torus of S of 2R. And we have scaling system. So this is the flavor. And this n has a endomorphism part and the framing part. And the endomorphism part is maybe this is trivial remark. This first summand endomorphism part is not the real algebra. So that's Pn. That's Pn. The adjoint representation, we have minus one. EY star is minus B1, right? So this is not the adjoint representation. We have to really get the different. So we replace this by adjoint representation, we just get the DAHA for type C. So this is not what I want to study. And second remark is, so Hiraku consider n or R constant and consider the study the corresponding Steinberg variety in finite case, finite dimensional settings. So this is what Kato calls the exotic nilpotent cone. And in this case, you have several parameters, and so he realized affine Hecke algebra instead of DAHA of type C with unequal parameter. So I think this is a good sign. And in fact, Kato himself already studied very similar to the infinite dimensional situation. He studied and he pointed out that some possible relation to C-check C. Okay, from now, I think I don't write the proof in detail, so every theorem is in quotation mark. Or maybe you can regard this as conjecture. So first of all, the commutative one, Coulomb branch. So this is, I think this is rather easy to show, but I don't study in detail. So you consider type dr surface and take n times and divide by Sn. And one of the key results for this, so if n equal 1, then so this part, this first sum disappears. First part is trivial. I think it is 0. And also SP2 is SL2. And in one of the BFN paper, the Coulomb branch for SL2 it was completely determined, and we get the dr surface. Maybe I wrote again the defining equation. So this is C squared is delta A plus square. So this is the usual one, but you allow R to be greater than 1 and R is equal to 0 cases is a little bit exceptional, and it's good. So once you know this, I think from this to this is not so big step. Okay, another result. Theorem, which I heard from the Taka Yoshida. It was my postdoc years ago. Private communication, so I don't know the detail. So for R equal 4 case, he studied the monopole operators. So in this case, as I said, this is not minuscule case. This is a small co-operator case. Small co-weight case. But somehow it is expected that you can write down the corresponding difference operator. And he identified this with Macdonald operator. Maybe only the first. Again, I'm not sure this is the correct notation. But anyway, I don't explain what is here. Check here. So it's explained. Okay. And the number of parameters. Maybe I record the number of parameters. So for n equal 1, we just have this is 4. You have 4 parameters. And n greater than 2, this is 5 parameters. And this corresponds. This R equal 4 case. I think that maybe where it is. So R equals 4 case because the first factor R equal 4 and n equal 1 because the first factor drops. So this scaling system disappears. And then you have 4 parameters. But for general n, you have 4 parameter plus 1 parameter. So this is 5 parameters. So it must. Okay. All right. So from this, I mean, of course, this is natural case that this is the case theoretical one. And the Coulomb branch. Homological one. No. For binary dihedral. Here. And this one. For R greater than 4. And for case theoretic one, so far I only convince myself for R equal to 4 case. So this is C check and C down. I expected from application. Spherical path. And I'm afraid I don't know what are the other cases. Maybe compared with the type A case. So if you consider case theoretic Coulomb branch for arbitrary R, maybe this is a new DAHA. And also I'm not sure what should be the algebra for R equals 0, 1, 3 case. Maybe 0, 1, 3 could be specialization of the R equals 4 case, but I'm not sure. This is usually opposite. If you increase R, then this is the subalgebra of the smaller one, and I'm not sure this is something compatible with no for sequence. So anyways, I stop. Thank you for that.